Okay, good afternoon, everybody. We'll go ahead and get started. So a couple of things to remind you about. The problem sessions are ongoing this week. So Monday's group had the problem session this morning. Thursday's group will have it tomorrow. No special requirements for the problem session. Just show up, be willing to work for a little bit. Please bring a calculator. You do need to have one. Doesn't really matter what kind of calculator, as long as it's not connected to the internet. That's kind of the only condition. Anything else is fine. Assignment 3 is all about electric field and electric forces. We've covered everything you need to know to do that assignment, except for question 14. Question 14 is a multiple choice question about the direction of an electric field. We're going to get to that, I expect today. If not today, then on Friday. If you don't want to wait until we get to that, if you flick forward in the notes, you can answer question 14. It's just identifying, comparing a picture. So you can go ahead and do it now if you want to look forward. Otherwise, you can do it after class today or Friday, whenever we kind of get to it. Any questions before we get started for today? No, it looks like we're in good shape. So last time we did lots of stuff about Coulomb's law and electric field. We'll do a little bit more about electric field today. And to start us off today, I picked an electric field problem that uses all the same concepts, but I just wanted it to look a little bit different, so you get an idea of how we can still use the same ideas, even if the problem doesn't look exactly like something you've seen in class. So this hopefully will start getting you used to the idea that even though problems, like a test problem, might look a little bit different, if you go through it step by step, hopefully you'll recognize that the physics is all the same, even if the setup looks a little different. So we're starting with an object of mass 2.5 grams. This part right here, m equals 2.5 grams. This is an enormous hint. This tells you that you can't neglect the weight. Okay, so if it gives you the mass, that's a hint right off the bat that you have to include the weight. The charge is 42 microcoulombs. We tie it on a string. When we tie things on a string, we know there's going to be a tension force. So this is calling back to a little bit of physics 1050 or 1020. It's put in an electric field. So now we know there's going to be an electric force. F is the charge times the field. The angle of the field is 30 degrees. The object is in static equilibrium. Static equilibrium means it's not moving, so the acceleration is equal to 0, both the x component and the y component. So there's a lot of information we know from reading the problem. We want to find the magnitude of the electric field and the magnitude of the tension in the string. So just like a physics 1050, 1020 problem, we're going to start by drawing a free body diagram. We're going to apply Newton's second law, and then we're going to figure some stuff out. So that's where we're going with this. Let's start with the free body diagram. So we've got our mass right here. The forces that act on it, the earth pulls down on it, so that's our weight force. We'll label that Fg. The string is holding it tied onto the wall, so that's a tension force. We'll label that T. And then this is a positive charge in an electric field. We know it feels a force, Q times E. The charge is positive, so the force is parallel to the electric field. It's up at an angle of 30 degrees. So there's our electric force. You don't have to put this in the diagram, but you can if you want to. Force equals Q times E, just as a reminder to yourself. We'll put on the coordinate system. We'll take positive x to be to the right, positive y to be up. You know we have to deal with components of forces. So let's draw the x and y components of the electric force. So the x component is to the right. The y component is up. And our angle in here, theta, is 30 degrees. Okay, I'm just going to zoom in for a little bit because I know my handwriting got a bit small there. Any questions to hear? So this is our free body diagram with our forces and components. Good, so let's move on to Newton's second law. Newton's second law says the sum of the forces, either in the x or in the y, is mass times acceleration. Let's write that down in both directions and see what we figure out. So I'll write down both equations, sum of the forces in the x and sum of the forces in the y. And let's see about applying those. So in the x direction, sum of the forces in the x direction is the mass of our charge, 2.5 grams, times the acceleration in the x direction. In the x direction, I've got my x component of the electric force and my tension. So Fx minus t equals mass times acceleration in the x, but that's equal to 0 because the thing's not moving. Okay, so acceleration is 0. I need to figure out my component. I'm going to put those workings down here. So the x component is adjacent to my angle. Fx is going to be f times cosine theta. F is the magnitude of the electric force. The magnitude of the electric force is the charge times the magnitude of the electric field. Good to hear. So my Fx is charge times E times cosine theta minus the tension equals 0. Tension equals charge times electric field times cosine theta. We're doing okay in this equation. I know the charge is 42 microcoulombs. I know the angle is 30 degrees, but I don't know E. So I'm sort of stuck with my x equation. So I'm going to stop. I'm going to move on to my y equation and see if that helps. So we know we're going to use both x and y. So we'll pause here and go to the y equation. In the y direction, I've got my y component of the electric force and my force due to gravity. So my y component minus Fg is mass times acceleration in the y, but it's not moving in the y direction, so the y component of acceleration is just 0. My y component of my electric force is opposite the angle, so I have to use sine. And the magnitude of my force, again, is Q times E. So my y component is Q times E times sine theta. Subtract my weight, that's m times g, equals m times 0 or 0. This equation looks really good. I know q, theta, m, and g, so I can solve for my electric field from this equation. I'm going to go ahead and find my electric field, then I'll have part A done, then I'm going to come back to part B and use this equation. So let's keep going with this one. Q, E sine theta equals mg. E equals mg divided by q sine theta equals. So my mass is 2.5 grams. So 2.5, got to put this in kilograms, times 10 to the minus 3 kilograms, times g, 9.81 meters per second squared, divided by q, 42 microcoulombs. So 42 times 10 to the minus 6 coulombs. Also divided by sine theta, which is 30 degrees. Okay, so there's all of our numbers. That gives us an electric field magnitude of 1168 newtons per coulomb. So there's the magnitude of the electric field. Had it asked to write your electric field as a vector, you could say 1168 newtons per coulomb at 30 degrees above the horizontal, because that's shown in the picture. So here's our answer to part A. Now that we have E, we can come back to this equation and find the tension. So my tension is my charge Q, 42 microcoulombs, times the magnitude of my electric field, 1168 newtons per coulomb, times cosine of the angle, which is 30 degrees. The tension in the string is 0.0425 newtons. Okay, any questions here? So what I did for the next few slides was, when we talked about electric force, we did a whole bunch of problems where we found the electric force doing a vector addition. We know we can find the electric field doing a vector addition. So I wrote all of those out for a homework question. It follows more or less the same process, but instead of doing k q1 q2 over r squared, you just do kq over r squared. So I'm going to post a bunch of those answers for extra practice for you. If as you're going through them, you have any trouble with it, let me know, and we can kind of talk about more of those. So the next thing we're going to get to, so far the only electric field we calculated was the electric field due to a point charge, kq over r squared. So we did that for our point charges. We know that when we have devices, we don't only have point charges. In fact, that's a little bit of a rare thing just to have a point charge. We have lots of wires. So this looks like a wire, a long straight wire. Sometimes, if we're making a solenoid, we make the wire into a circle. Sometimes we have solid spheres or hollow shells. And sometimes we have planes. We can have lots of different geometries of conductors that are charged. If these conductors all have charges, they all make electric fields. So we don't only get electric fields around point charges, we get electric fields around anything with charge, regardless of their shape. What we can do is you can use a calculus method to calculate the electric field around all of these shapes. If that's something that tickles your fancy, then you might like Physics 2055. We're not going to do it in this course, but you can do it. If you're super interested, you can also follow through with the book. So it's important to know that anything that has a charge does have a field. We're going to jump right to this plane of charge, and we're going to focus on this for a while. So this is the one we're going to work on the most. It's the most applicable to this course and kind of what comes after Physics 1051. So when we have circuits, you're probably familiar with resistors, but circuits are also full of capacitors and inductors. Capacitor is a device that we're going to talk about for a little while. We're going to spend some time at it. And a capacitor is a device made out of two small plates of charge, or two small planes of charge. So a plane of charge is the fundamental basics for making a capacitor. So we're going to talk about this plane of charge first, and then create a capacitor from it. So if we talk about a plane of charge, what we mean by that, in an ideal sense, is that it's infinite in 2 dimensions, and it's thin in the 3rd dimension. Okay, so if we put a coordinate system on it, where z points up, x points to the right, and y points into the page, then it's infinite in x and y, goes on forever, and it's thin in the z direction. So this is what we mean by an infinite plane. Our infinite plane has a charge q. It's typically more useful, because it's an infinite plane, it's typically more useful to talk about something called the charge density. Charge density has a symbol of sigma. So this is the Greek letter sigma. It is surface area charge density. So it's charge divided by area. Q is charge, A is area. It has units of coulombs divided by meters squared typically. Okay, so charge density is a number we're going to work with primarily. If we want to define the electric field around this plane of charge, what we would do is we would recognize that it is full of charges. Let's say that they're positive charges. And then this is an edge view of that plane of charge. So this is our 3D view, and this is our 2D view for our edge view. We know that electric field goes away from a positive charge. When we have this plane of charge, what we find is pretty interesting. What we find is that all the left-right components, they all cancel, and we're only left with components that point straight out. And remember, this goes on forever in the X and Y direction. In our 2D view, that's a little bit easier to look at. It points straight out. When you do the calculus to figure out the equation for the electric field, what we find is that the electric field near a plane of charge is the charge density sigma divided by 2 times our constant epsilon naught. Remember, epsilon naught is what we call the permittivity of free space. That's a constant that has value 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. So that's a result we get. The direction of the electric field is perpendicular to the plane. And then we have two choices. It either points out of a positive, like the picture we've drawn, or into a negative. Okay, so this tells us the electric field around a plane of charge. What else is interesting about this result? So it's perpendicular, points straight out, doesn't point left or right. Notice that it doesn't depend on the distance from the plane. Okay, so it's constant everywhere. So whether you're in close or you're far away, the electric field has the same value. So that's an interesting result as well. Okay, questions here? Yeah.
Why is it 2 now? Like, why do you want to know by 2 in?
Why is it 2 here?
Yeah.
It comes from the calculus. Yeah, okay. You can sort of think about it as coming from the fact that there are two sides. The electric field comes out of both sides.
That is for non-conducting materials?
Doesn't matter if it's conductor or non-conductor. Yeah, so just around it. If you downloaded the notes, the next slide is just a picture I nabbed from the textbook that's just nicer than my drawing, so I wanted to include that in your notes for you, just because I know my drawings aren't nearly as good as the book ones. So that's around a plane of charge. So the next thing we want to do is make our capacitor. So the definition of our capacitor is it's an electrical device, and we use these devices to store electric energy. Let me show you. So this is just a graphics card. I asked John if he had anything out of a computer for me, and he gave me this. If you've opened up your computers, you've probably seen something that looks like this inside of it. If you open up anything electronic, it's got something like this inside. So I'll zoom in just to make it a little easier to see. See all these round ones here? Those are all capacitors. And what these little devices do is we hook this up to a power supply, a battery, or you plug it in the wall. These things store up electric charge, and when they store up charge, they store up electric energy. We're going to circle around energy as we go through. Did you ever notice, so I have always been kind of a tinkerer. If stuff breaks, I do like to take it apart and see if I can fix it. I don't know if anybody else is the same. But if you have your electronic devices, if you look on the back of them, there's a big sticker. It's usually in red with big font, and it says, "Do not open." Anybody ever noticed those before? I open them anyway. The reason you shouldn't open them is because of these, right? These are fully charged up. They store a lot of energy. If you put your screwdriver in one of these, you can get yourself a big shot. That's why you shouldn't open this stuff up. It's not just about, voiding your warranty. You could really hurt yourself if you do this because there's so much energy inside of it. So that's one of the reasons you're not supposed to open this stuff up anyway. Okay. So there's our capacitors. Our definition, how we create a capacitor, is we take two planes of charge, plus Q and minus Q. We put them a distance d apart, and we label d in the picture. So d is your distance between the two planes. And that's what's called a parallel plate capacitor. So one charge is positive, one charge plane is negative. I'm going to call the one on the right the positive plane. So I'll call this one plus Q, or plus sigma, and this one is going to have the negative charge, negative Q. The amounts of charge are equal, but they are opposite signs. So that one is plus whatever, that one is negative whatever. Every plate has the area A, and the charge density is the charge divided by that area A. Okay, so that's our capacitor, that's our charge density. And now the question is, what's the electric field around these plates? And this is the thing that's going to let you answer question 14 from the assignment. So we're going to answer that question as we go through. So if we have two plates, we can call them 1 and 2 if we wish. I'll label this a 1, this a 2. This is my 3D picture, and this is my 2D picture, or my edge view. So this one is plus Q, this one is minus Q, this is plate 1, this is plate 2. Let's kind of get a sense of what's happening here. So this plate has all the positive charges. This one has the negative charges. So plus, 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 minus, 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 minus. That's not showing up super well, sorry. So this plane, I just drew a bunch of negatives on this plane, and I drew a bunch of negatives on this one because this is the negative side. Okay, we'd like to find the electric field. I say near the plates, so I'd like to find the electric field in 3 places. I want to find the field out here, so to the left of plate 1. I'd like to find the field in between the 2 plates, and I'd like to find the field to the right of plate 2. So if I find each of those 3 spots, it's going to give me the field everywhere. So that's a good descriptor of the electric field. Let's think about how we're going to do this. So plane 1 is a positive charge, a positive plane. We know it makes an electric field that points outward. So let's draw the electric field right here due to this plane of charge. So I know I need to start here and go outward. So there's my electric field due to plane 1. I know that it has a magnitude of sigma over 2 epsilon naught. And if I put in my coordinate system, plus x to the right, plus y to be up, I know the direction is to the left or in the negative x direction. So as a vector, that would be negative I hat. Okay, so this is the electric field due to plane 1 only. I've got 2 planes, I know there are going to be 2 fields, and get the total field, I'm going to add them up. So the other vector I need, what is the electric field right here due to this negative 1? Well, I know that my electric field points into a negative. So my electric field due to plane 2 points in toward plane 2. So that's E2. It has a magnitude of sigma over 2 epsilon naught, and it points to the right, so that's plus I my net electric field, E, is the sum of those two individual fields, E1 plus E2. So in this area, E1 plus E2 equals 0. Okay, so out here to the left of plate 1, those two fields cancel. Equal magnitude, opposite sign, so they sum up to be 0. You okay there? All right, let's do over here on this side. Probably you have a guess of what that's going to turn out to be. So my electric field, due to plane 1, is going to point away from plane 1. Here's E1. It has a magnitude of sigma over 2 epsilon naught. It points to the right, so it has direction of plus I hat. So there's the electric field at this point, due to this plane. And the electric field at this point, due to this plane, points into the plane because it's negative. E2 has a magnitude of sigma over 2 epsilon naught. It points to the left, so the direction is negative I hat. To find the total electric field, we sum those two up. We see that that's going to be equal to 0. So my net field so outside the capacitor, the electric field is 0. Let's get to inside the capacitor. So I'm going to do the same process. What's the electric field at this point due to this plane? Well, it's a positive, so the electric field points away. E1 equals plus sigma over 2 epsilon naught I hat. So there's the electric field due to plane 1. Due to plane 2, the electric field points into the plane, so that's also to the right. E2 equals plus sigma over 2 epsilon naught I hat. So my net field is the sum of those two. Equals sigma over epsilon naught times I hat. So to get the total field, you add those two fields together. Okay, questions about any of this stuff?
Wait, so the one on the right is, that's negatively charged or is it positive?
This one is a negative charge, this one is a positive charge. And our electric...
Positive is attracted to the negative, and then the negative... Why is there two?
So the way we think about it is electric field lines, these red ones, they go away from the positive, right? So these red arrows show the electric field due to this positive one. It points away from it.
Right.
The electric field due to the negative one, the blue one is the blue arrows, they point into the negative. So that's where those directions come from. Away from positive or toward negative.
Or isn't the negative just like a charge in itself? Does it go out and then come back or something?
No, so the electric field, when you're drawing an electric field, put your pen at your point.
Yeah.
You either go away from a positive or toward a negative. To the right is toward negative.
Okay.
Okay, we can talk about this more after if you want to. You sit down with the pictures. Okay, so let's write down our answer. So the electric field near the plates of a capacitor are E equals sigma over epsilon naught. You remember that sigma is charge divided by area. I'm going to say, instead of saying it's to the right, because that's very specific, I could turn this thing sideways, I'm going to say from positive toward negative. Okay, so then that applies to however we turn around our capacitor. This is the electric field between the plates, so I'll put that in brackets. And then we'll say and E equals 0 outside the plates. So there's a summary of what we just found. So now I'll just kind of put in a little bit of context of real versus ideal. We said that when we had planes, they were infinite, so they go on from infinity up and down and back and forth. Infinite is not something we can achieve in the real world. Okay, infinity is not something we can get to. So ideal plates, so let's say the length here is L, and the distance is D. And if these are square, it would be L by L. So for infinity, ideal plates, that's what we get for this result. So this is for an ideal plate. For real plates, what happens is your electric field up near the edges is not quite equal to sigma over epsilon naught. There's a little tiny bit of variety around the edges. And instead of the electric field being straight, it sort of bends at the edges. So what we do in practice, so when technicians are making capacitors, because it is important to make them well, you want them to work and you want to be able to know what the field is. What you do to make them as good as possible is you have this length here a lot bigger than this separation. This gets our real plates to be close enough to ideal. We're happy enough with that. These are the kinds of plates we're going to work with. If you go into capacitor making, you might have to deal with the fact that you'll have these effects, but we're not going to talk about it in physics 1051. That would be more like in a manufacturing thing. Yep.
Is there much reason to have the charge being repelled by having like two of the identical plates? Like we have positive on both sides. Would you always want the capacitor to have the charge or the field exist within those two plates rather than outside?
Yeah, it's got to be inside. Yeah, because it's going to be part of a circuit, and when we get to our circuits later, we'll see how when we connect it to a battery, it will make itself with one plate positive and one plate negative.
Yeah, so you've never wanted to have two, you're never going to build a capacitor with two of the
No.
identical plates.
That wouldn't even be a capacitor. I'm not sure what it would be, but it's not a capacitor.
Color, I guess. Would
Yeah. Okay, so we're good to keep going. So let's do an example of something you might see. We'll do a few examples now about these. So we say that a capacitor is made from 1.5 centimeters square plates. So we might call 1.5 centimeters L. I like L for the side length. So we'll call this L. We'll call this L. The left plate is positive, the right plate is negative. So I'll put on some pluses here. Put on some negatives here. Okay, so now we know about those. If the field between the plates is 2 times 10 to the 6 newtons per coulomb, find the charge on each plate. Okay, so we know the field E, we want to find the charge Q. We're not asked to draw the electric field, but it's not a bad idea to do that anyway. So the electric field is going to be constant between the plates, and it goes from the positive to the negative. So the field between the plates looks like this. And then sometimes we would also know the plate separation D. So there's a picture of what's going on. There's the field. We want to find the charge. So let's remember that the electric field between the plates, E, has a magnitude of sigma over epsilon naught. So that was the result we found on the previous page. That means we can find the charge density sigma. It's E times epsilon naught. Put our numbers in. 2 times 10 to the 6 newtons per coulomb times 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared. We get that the surface area charge density is 1.77 times 10 to the minus 5 coulombs per meter squared. Okay, so there's our surface area charge density. So there's our sigma. We weren't asked for sigma, we were asked for the charge on each plate. So we remember that charge density is charge divided by area. Yeah?
I thought there was a 2 in the formula.
So when I had the 2 up here in this equation, remember sigma over 2 epsilon naught was for one plane. When we put the 2 planes together, we have to add them up, and that's where the 2 went. Okay, good catch. So now we're trying to find our charge Q. We remember that sigma is charge over area. Area of a square is just the side length squared. So that means Q is sigma times L squared. Sigma was 1.77 times 10 to the minus 5 coulombs per meter squared, times by L squared. L is given in centimeters, should convert that to meters. Don't forget to square it. And we get 3.98 times 10 to the minus 9 coulombs. So that's the amount of charge on each plate. This charge is positive, that charge is negative, and that's the amount of charge. Any questions there? Yep.
What if in this question you give us the volume and the density? Can we calculate the charge density? Surface area?
Volume charge density is something we're going to come to. The reason that doesn't work here is because these plates are thin, they don't have a volume, so that's why we wouldn't do volume charge density here. Yep.
The surface area charge density is calculated using the charge from one of the plates?
Right, so each plate has a charge and an area, so you do the charge over the area of just one plate. Yeah, good clarification. So we still have some time left. Let's get started on another capacitor example. So in this example, a capacitor is formed by charging 2 5-centimeter plates. When it says here, this is just a bit of wording. 2 5-centimeter plates means it's 5 centimeters by 5 centimeters. It's a square plate where each length is 5 centimeters. That's what that wording means. To equal and opposite charges of 1 microcoulomb, so there's the side length, there's the charge on each plate, and separating them by 1 millimeter, there's our plate separation. So our plates have to be positive and negative. I'll call the one on the left negative, minus Q. I'll call the one on the right positive, plus Q. I'll draw in my pluses and minuses. You don't strictly have to draw in these charges. I like to draw them just because it helps us visualize the electric field. We know which way to draw it. Our side length L is 5 centimeters. So L, 5 centimeters. Our plate separation D is 1 millimeter. And Q is equal to 1 microcoulomb. So there's our information. Part A, pretty straightforward. Find the electric field between the plates. We know that the magnitude of the field E is the charge density divided by epsilon naught. So sigma over epsilon naught. You could calculate sigma first if you wanted to. I think I'm going to go straight to symbols. So Q over area divided by epsilon naught. The area is the area of a squared, so that's L squared. So I've got Q over L squared times epsilon naught. 1 times 10 to the minus 6 coulombs divided by 0.05 meters squared is 8.85 times 10 to the minus 12 coulombs squared over newtons meters squared. So my electric field has a magnitude of 4.52 times 10 to the 7 newtons per coulomb. Careful here, when it asks for an electric field, you have to remember that electric field is a vector, so to have a complete answer, you do have to put in the direction. So we'll make it a vector, and we'll say from positive to negative. And then if we wish, we can draw that in our diagram.
Would you ever designate it as just a negative or positive sign? Is it just for clarity, is it positive and negative?
Yeah, I might give the plus and minus in the diagram, or you might draw it for yourself. Could go either way. Yeah. Okay, so now we've got some more stuff going on. If we release an electron from the negative plate, so the first thing I'm going to do is just draw a 2D picture down here. So here's my negative plate. And I've got my electron. That's a little negative charge. I'm going to release it from the negative plate. And then we ask what happens to it. Plus, 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 plus. So I've got this negative charge here. When I let it go, what's going to happen to it?
It's gonna go to the right.
Yeah, it's going to fly over to the positive plate, right? So it's going to start to move. It's an electron. It's in an electric field. It has a charge and a field. It's going to feel a force. We know F equals ma. We know a bunch of kinematics. This is the stuff we're going to throw at this problem. Okay, so that's where we're going to go with all of this. I'm going to put my electric field picture on top here because it is an electric field problem. So there's my electric field. I'll put in a coordinate system. I'm going to take positive x to be to the right, positive y to be up. I'm releasing it from the negative plate, so my initial velocity is equal to 0. Okay, I release it, means I release it from rest. Find its acceleration, a equals, and a is a vector, so I'm going to put my vector sign on there. So let's think about what's happening to this electron. Electrons are very light. That means that in general, we will be neglecting the weight, and I am going to neglect the weight here. So that weight is much smaller than the electric force. If I draw the force on the electron, I know the electric force is going to pull it or push it to the right. So there's my electric force. I'm going to write Newton's second law. The sum of the forces is mass times acceleration. The only force I have is the electric force. My electric force is charge on the electron times the electric field. Mass times acceleration. You good to hear? So the only force that we care about on the electron is the electric force. We don't care about the weight because it's so tiny compared to the electric force. I want to find my acceleration, so that's going to be the charge on the electron times the electric field divided by the mass of the electron. So let me put in what I know here. My charge on my electron is negative of my fundamental charge, so minus 1.60 times 10 to the minus 19 coulombs. My electric field is 4.52 times 10 to the 7 newtons per coulomb. You see that I've got a vector here in my equation, okay, and I put the vector in on purpose because I'm trying to find the acceleration vector. So I better be careful to write this as a vector. The direction of my electric field is from positive to negative, or to the left. So that's negative I hat. Okay. If you chose to write in magnitudes and find the magnitude of the acceleration, and then look at the diagram and see that it accelerates to the right, you know, if you did it that way, that's fine. I'm just going with the vector treatment here in this one. We're going to divide it by the mass. 9.11 times 10 to the minus 31 kilograms. Our acceleration is equal to 7.94 times 10 to the 18 meters per second squared in the x direction, or I hat. So it accelerates to the right. We knew it was going to accelerate to the right because it's repelled from the negative plate and attracted to the positive. Okay, any questions about that bit? Okay. Part C, find the speed when it reaches the positive plate. So we know it's traveling from the negative towards the positive. It's traveling this distance d. The initial speed is 0, the acceleration we just found, and we want to find the final speed. So we can use our kinematics again. We know v squared, our final speed squared, is our initial speed squared times 2 times a times the distance traveled. So our final speed is going to be the square root of vi squared plus 2 times a times d. Vi is equal to 0, so we've got the root of 2 times a times d, square root of 2 times 7.94 times 10 to the 18 meters per second squared, times d, that was 1 millimeter. With the square root. So that final speed is 1.26 times 10 to the 8 meters per second. So we'll put the word fast here afterwards, because it is going pretty fast. We're getting up there to about 1/3 of the speed of light. So it's fast, but it's not impossible. If you did get an answer that was bigger than 3 times 10 to the 8, you would know that that was the wrong answer, okay? And you would go back and double check your algebra, because we're not going to have anything going faster than the speed of light. Okay, questions to here? Okay, then part D, how long does it take to travel this distance? So how much time does that take? That's going to be another kinematics equation. So part D is how long does it take? Well, we know that V is equal to V initial plus A times T. So T is going to be V minus V initial divided by A. So that's speed 1.26 times 10 to the 8 meters per second, subtract 0, divided by 7.94 times 10 to the 18 meters per second squared, gives us a time of 1.59 times 10 to the minus 11 seconds, very fast. So these electrons do move really fast. Doesn't take them long to get anywhere, and they're going pretty fast when they get there. Okay, any questions there? And then for a homework question, I've just got repeat if this is a proton. So that'll be the same steps, but we know it's a different charge, a different mass. So we'll leave it there for today. Because today is a Monday schedule,